Welcome back to my channel. Today I am going over three important circle-related theorems for my friend's daughter Luna, who is studying these theorems in class. I hope all of you find this video useful, just as Luna may. We will follow the same lecture flow step by step, and I will keep the transitions light so the proof ideas stay front and center. This deck isolates three related circle theorems: Tangent-Chord Angle Theorem, Tangent-Secant Theorem, and Intersecting Chords Theorem. Because there are only three cards, each one gets a larger figure and a fuller proof story. First theorem, Tangent-Chord Angle Theorem. The angle between the tangent line and chord AB equals the far inscribed angle on the same chord. Let beta be angle TAB and alpha be angle ACB. Join radius OA and radius OB. Radius OA equals radius OB. So triangle OAB is isosceles. Radius OA is perpendicular to the tangent line A. Hence angle OAB equals 90 degrees minus beta. So angle AOB equals 180 degrees minus twice angle OAB. Therefore, angle AOB equals 2 beta. The same chord AB gives angle AOB equals 2 alpha. So 2 beta equals 2 alpha. Hence, beta equals alpha. Keep that angle match in mind, because the next theorem turns the same tangent chord idea into a power identity. For a more advanced mental picture, think in the spirit of Newton and geometric limits. Move point C toward point A on the far arc. Because chord AB stays fixed, alpha stays constant. In the limit, segment AC approaches the tangent line A, and segment BC approaches segment BA. So the limit of alpha is beta, and to an advanced eye, alpha and beta should feel naturally the same. Second theorem, Tangent-Secant Theorem. The memory line whole times external equals t squared, or Wet2. Now keep the tangent-chord theorem alive and move to the secant power theorem. Start from the basic picture with tangent PT and secant PAB only. Join chord TA. Join chord TB. By the tangent-chord theorem on chord TA, angle PTA equals angle PBT, both alpha. At point P, the angle TPA is the same as the angle BPT because they use the same secant line through point P. Hence, triangle PTA is similar to triangle PBT. Write the ratio PT over PA equals PB over PT. Cross-multiply the ratio. Therefore, PT squared equals PA times PB, so the memory form is whole times external equals T squared, or simply WE equals T squared. Alternate explanation 1. From the triangle similarity we already proved, angle PTB equals angle PAT. Call those equal angles beta. Now extend segment PT through point T to the new point P prime. Then angle prime TB equals angle TAB by the tangent-chord theorem on chord TB, so their supplementary angles, the two beta angles, are equal too. Yet another way to see it is by angle chase. Angle TAP equals angle ATB plus alpha, and angle PTB equals angle PTA plus angle ATB, so both equal angle ATB plus alpha. So the equal alpha and equal beta relations are both natural consequences of the tangent-chord theorem, and as a result the Wet2 theorem is proved. Next we move inside the circle and use the same similarity instinct on intersecting chords. Now pause on the finished theorem and just watch the picture move. The outside point, the secant, and the tangent can all shift, but the relation still survives. Whole times external still matches the tangent square. That is the point to remember. This is a general theorem, not a lucky diagram. Third theorem, Intersecting Chords Theorem. Inside the circle, the two products match. U times V equals R times S. Now move inside the circle to the intersecting chords theorem. Start from the basic crossing chords picture with chord AC and chord BD only. Draw auxiliary segment AD. Draw auxiliary segment BC. Compare triangle APD with triangle BPC. Angle ADP equals angle BCP because both stand on arc AB. Angle DAP equals angle CBP because both stand on arc CD. Angle APD equals angle BPC as vertical angles. Hence, triangle APD is similar to triangle BPC. Write the ratio AP over PD equals BP over PC. Cross multiply the ratio. Therefore, AP times PC equals BP times PD. That closes the circle power triptych. Now pause on the finished inside product theorem and watch the chords move around the circle. The crossing point can slide, the chords can tilt, and the triangles can change shape, but the product law still stays in place. That is what makes the theorem feel structural. It does not depend on one frozen picture. That finishes this short course on three important circle theorems. We have seen one family of angle and similarity ideas reappear in three nearby pictures. If there is anything you want me to review next, leave a remark below. And subscribe to the channel if you find this kind of video helpful. Finally, good luck to Luna.